Hello, everyone. Welcome back. So today we're going to be hitting the last piece of information necessary for the ACS exam. So everything in the class so far can show up on the ACS exam, and it probably will. And so you've actually learned a lot more than you probably think you have, but there is one set of things that I did not explicitly talk about throughout the semester that I wanted to talk about today. Because I know that this was supposed to be reviewing challenging concepts, but considering the fact that a lot of those challenging concepts are going to be a little easier on the ACS exam, I figure it's better to give you the full exam coverage. That way you can get some of these easier questions than to rely on really understanding some of those harder ones. And the real main thing that we did not go over during class throughout the semester, but we do need to go over now, is going to be physical properties. Right, because sometimes I have asked you about these physical properties, but in such a way that it has related to the material that we're talking about. But today we're really going to look at physical properties and we're going to talk about everything that alters them. That way, when you're asked about these things on the ACS exam, it's really quite simple to answer. All right, so just buckle in. This is going to be a super simple lecture. It's going to feel like the first time in a while that you're like, oh, all of this makes perfect sense. So let's just start out by talking about boiling point and melting point, right? And so we're going to start out by looking at size influence on boiling point and melting point. So when you were in Gen Chem, you probably talked about boiling point and melting point quite a bit. Here in organic, we're going to talk about it very simply. All right. Boiling point is just the temperature at which something boils at atmospheric pressure. Melting point is just the temperature at which something melts at atmospheric pressure. And so we're just going to look at these and talk about the trends and why they exist the way they do. So, thinking about simple alkanes, right? CH4, methane. If we look at its boiling point, we would see that its boiling point is negative 162 degrees Celsius. It generally exists as a gas. Same thing with something like propane. But what we'll see is that for propane, the boiling point has drastically increased to negative 42 degrees Celsius, right? Lastly, if we take a look at something even longer, such as hexane, we would see that our boiling point increases even more to 69 degrees Celsius. And so essentially, this trend is the same as what you saw in Gen Chem, right? As we go from left to right, we are seeing an increase in molecular weight. And so boiling point increases as molecular weight increases, right? It's a very simple trend. So if you see something that has more molecular weight, it's probably going to have a higher boiling point because it's harder to rip things out of the solution if they're heavier. The same thing is somewhat true with melting point, right? It's just not as simple as that. If we look at the melting points of each of these, the melting point of methane is negative 183 degrees Celsius. The melting point of propane is negative 188 degrees Celsius. But then the melting point of hexane is 95 degrees Celsius. So generally speaking, the trend is somewhat similar. All right. So melting point slightly increases with molecular weight. The only thing is, this is not always as simple, right? We will talk about why here momentarily. And it'll make sense on why propane and methane have some wonky melting points momentarily. But essentially, as molecular weight increases, both of these factors normally increase. All right. So let's take a look at what happens in terms of other groups being added, because these are just very simple hydrocarbons, right? Let's think about the influence of IMFs, right? So let's take hexane as a good baseline for what we're looking at, and then let's just add on an oxygen to this, right? And we'll do one as a ketone and one as an alcohol in the same position, the 3 position, let's say. So, hexane's boiling point, which we already know is 69 degrees Celsius, and we already know its melting point is negative 95 degrees Celsius. As we add on this oxygen, not only does it change the boiling point because we add a little bit more mass, but it's a massive change in boiling point up to 123 degrees Celsius, and it's a massive change in melting point to negative 55 Celsius. Furthermore, if we look at it as the alcohol, it's an even larger increase in boiling point, 135 degrees Celsius, versus the melting point of negative 57, which is generally the same as the hexane threone, pretty close to it at least. What the trend we're looking at here is as we go from left to right, stronger IMFs contribute to higher melting point and boiling point, right? So, thinking about what this means for us. Well, if we look at hexane, if hexane's interacting with itself, it's just kind of stacking and doing some LDF or van der Waals, right? So this is only London dispersion forces slash van der Waals. And as we know, these interactions are relatively weak. On the other side of this, as we look towards our hexanone, right, if this is interacting with itself, how's it actually interacting? Well, the oxygens have a partial negative charge, right? Because they're pulling a dipole on the carbon, making it partially positive. As we know, as you bring these charges closer to one another, they are attracted, right? So these are attracted by dipole interactions. And so that attraction leads to a higher boiling point and generally a higher melting point. Okay? But with that idea in mind, we also have to look at what the alcohols are doing. Well, the alcohols have an even stronger interaction that they're doing, which is hydrogen bonding. Right? These hydrogens in here are going to have this hydrogen bonding interaction with the oxygen because we know that the oxygen being partial negative, the hydrogen being partial positive, and the fact that it's an oxygen that can do hydrogen bond accepting and the hydrogen can do hydrogen bond donation, we end up seeing this hydrogen bonding in between, which is stronger than dipole-dipole or van der Waals. And so when we're thinking about boiling, what we're looking at is if you have a beaker that is filled with hexanes, in order to boil one of these away, right, get it to leave, all you have to do is overcome van der Waal forces. All right, so for this to boil, I have to overcome the relatively weak LDF slash van der Waals, right? So that's all you have to break up. Versus if we're looking at a solution of the hexanol, right? If we wanted these alcohols to break apart and for this one to get boiled away, we would have to overcome hydrogen bonding. Which is difficult. All right. So essentially, the more IMFs that something has, the stronger IMFs, the harder it's going to be to boil it, meaning it's going to have a higher boiling point, and it's usually true as well with the melting point. All right. But the thing is, these IMFs are affected by other things. So, to go a little deeper, this is the one that is a little different from some things you learned in Gen Chem. A lot of this so far has been Gen Chem review. But now we're looking at shape, right? Because shape also affects physical properties. So, let's take a look at two molecules that are somewhat similar, but they end up being drastically different in terms of their physical properties. So we have benzene here on the left, and then we have toluene here on the right. So benzene has a boiling point of 80 degrees Celsius versus toluene's boiling point is 111 degrees Celsius. And this trend makes sense based on what we've seen, right? Looking from left to right, we got bigger size or molecular weight, which means it must have a higher boiling point. Very simple, it makes sense based on what we've said so far. But if we look at the melting point, benzene's melting point is 5 degrees Celsius, but then toluene, which we would expect to be a little higher, is actually negative 93 degrees Celsius. And so this is the opposite of what we would expect, right? We'd expect that the melting point of toluene, being a higher mass, should be higher. However, it is drastically lower than that of benzene. The question just becomes why? Well, it's because of shape. If we look at benzene in general, all of the atoms surrounding it, they are all sp2 hybridized. What this means is that benzene is completely planar, right? It is flat. So what we can do is we can think of it like it's just a flat board, or like a line in Tetris, if you wanted to call it that. Right? So this thing is completely flat. If you take multiple benzenes and you stack them on top of each other, what is that going to look like? Well, each of these flat pieces is going to stack perfectly with the other flat pieces. And so what that gives us is the interaction between any two of these benzenes is going to be a perfect surface interaction, right? Which essentially just means we have a higher or stronger, we'll call it, LDF interaction, right? Because the only thing that London dispersion forces bank on is the fact that the atoms will be close enough that they can interact in some way, shape, or form. And so looking at benzene, it essentially is able to get these really nice LDF interactions because it sits flat on itself. Toluene, by comparison, has one thing that benzene does not. It has this carbon right here, which is sp3 and tetrahedral. So unlike benzene, toluene is not completely flat, right? This tetrahedral center makes it to where it actually is 3D. And so if we're thinking of this, similar to what we saw with the benzene, we would say that this kind of looks like a board that's relatively flat, but there's like this big old, uh, I guess, knob in it that is not completely flat, right? This represents sort of that tetrahedral CH3. So, what does this do? Well, whenever you try and stack these, it ends up being a worse stacking interaction. Because if you take one of these not so perfectly flat boards and you try and stack on it another not so perfectly flat board, you end up with the only places that surface interactions are happening are here and here, right? And that's not to say that good surface interactions can't happen, right? You could have another one of these that sits right here. But then the next one that comes in is also going to have to be like this. So overall, it has much less surface interactions, which means worse LDF or weaker. Essentially, this interaction means we're going to have a lower boiling point and melting point. All right, so we'll call it worse shape for interactions equals lower boiling point and melting point. And where this is also true, where you could actually see it, is if you take something like butane versus the isobutane, I guess you'd call it. Essentially, this one, the butane, has a higher boiling point and melting point, and then the isobutane has a lower boiling point and melting point. Right? So shape interactions really matter, and the reason that the isobutane has a lower boiling point and melting point is because all of these carbons on the outside are branching off, and so it ends up being this very big steric thing where not much is able to interact, versus this one that's more linear, just has branching along the way that's easily dealt with. Now, that being said, keep in mind that the reason toluene's boiling point is so much higher than benzene's is because it has a higher molecular weight. And so that higher molecular weight ends up offsetting that, but it doesn't offset the melting point. Shape matters a lot in terms of melting point. All right, let's look at the next piece of information that affects our boiling point and melting point. That is electronegativity. So, first thing we gotta do is we have to think about oxygen versus nitrogen. Right? If we look at the electronegativities of each, oxygen has an electronegativity of 3.44. Nitrogen has an electronegativity of 3.04. And one of the things that this actually ends up doing is if we take a look at two different structures that are the exact same, the only difference is we replace an oxygen with a nitrogen, right? So that being ethanol and ethylamine, we see a major difference in physical properties. With ethanol, the boiling point is 78 degrees Celsius, versus with ethylamine, the boiling point is only 16 degrees Celsius. So the question is why? Well, if we take a look at each of these, the first thing that we notice is looking at ethanol, right? We can say that this has a pretty strong dipole being pulled from the hydrogen towards the oxygen. And what this leads to is some relatively strong partial charges. On the other hand, if we wanted to look at the same idea just with ethylamine, right, we can draw out one of these NH bonds. The dipole is now much weaker, right, because it is not as electronegative. And that also means that these partial charges are weaker. Why this matters is because it's the same thing that we talked about with the IMFs beforehand, right? If we look at what these can do with each other, the ethanol can end up forming some hydrogen bonds with another ethanol. When we do this, these hydrogen bonds are really strong, right? Because they're interacting between these highly charged or highly partially charged species, right? So these are very strong hydrogen bonds. But not all hydrogen bonds are made equal, right? If we take a look at our amine now, and we draw the same set of interactions, we see that these nitrogens can still hydrogen bond, right? But they are hydrogen bonding, whoops, with relatively weaker interactions, right? Because when we look at this, we would say weaker dipole equals weaker charges, which equal weaker hydrogen bonds. Because hydrogen bonds in reality are just another way of looking at dipole-dipole interactions. It's just normally the dipoles on the hydrogens are much stronger than on anything else. So these differences in hydrogen bonds actually change the boiling point drastically, right? Because we would say that the strong hydrogen bonds are overall a stronger IMF, intermolecular force, which means that it also has a higher boiling point. All right. So that's something to keep in mind as we look through these physical properties, right? The things that really tune them are size, bigger means higher boiling point, higher melting point. IMFs, the stronger the IMFs, the higher the melting point and boiling point. Shape matters. So if you have something that's completely planar, it's going to be able to interact better than something that is not entirely planar. And then last but not least, still in the realm of IMFs, electronegativity does matter in these cases. One last thing that I wanted to bring up that is relatively important here is something to remember, and it has to do again with shape and such. If we look at something that has the exact same atoms, uh, all the exact same uh, mass as well, except I guess this one is -2. If we look at the difference in boiling points here, the boiling point of the dimethyl ether would be -24 degrees Celsius, whereas the boiling point of this acetaldehyde would be 20 degrees Celsius. And this is another idea of shape, where looking at this, we have this sp2, which is planar. It's easier for dipoles to interact, right? Essentially what that means is stronger IMFs equals higher boiling point. And you'll even notice that this acetaldehyde right here is even better in terms of IMFs than the ethylamine because it has a slightly higher boiling point. And that's again because of that a lot easier to interact means stronger intermolecular forces. All right. So physical properties of boiling point and melting point have a couple things that tune them, but they're all relatively simple and things that you've probably heard before. So just keep those in mind whenever you're looking at some of these ACS questions, because if they ask you which has a higher boiling point, you should be able to deduce it given these parameters. Next thing we're going to want to talk about is water solubility. So, back in Gen Chem, a lot of times you were looking at things like salts, right? Sodium chloride and water. What does that look like? Well, essentially, it looks kind of like some of these things that we drew when we were talking about SN2, where we have our sodium cation, and it can get surrounded by water, right? And as it does, essentially those oxygens that have the partial negative charge in water are able to stabilize the corresponding sodium, right? All we're saying is that the partial negative oxygen stabilizes the plus charge, right? On the other hand, the chloride that also exists here is going to be stabilized by water in a slightly different way, but still very similar, where now it's just the other piece that is doing it, right? Our partially positively charged hydrogens are able to surround the chloride and stabilize it, right? So essentially what we say here is that the partial plus hydrogen stabilizes the minus, right? And so water solubility runs off of a single rule that ends up going over the entirety of water solubility of any compound you're looking at. And that is essentially favorable interactions with water equals water solubility. So these favored interactions of these ions interacting with the water is what ends up making them water soluble. Now, when we look at organic things, the story is a little bit tougher to deduce. Because first, there is a very simple rule in organic chemistry, which is, like dissolves like. And we can say that all alkanes are completely insoluble in water, right? If we look at something like hexanes and a water molecule, there are no favorable interactions. So with that in mind, there's no reason for these to actually mix, right? This is where we get two different terms that you're going to see pop up whenever you're talking about water solubility. You're going to see hydrophilic, right, which means lover of water. This is essentially something that has favorable interactions with water. And then we have hydrophobic, which is a hater of water. This is something that does not or doesn't have favorable interactions with water. Right, we would say that alkanes are hydrophobic. They do not like water because they would rather be around things that they have favorable interactions with, which are other alkanes, versus water being hydrophilic, it likes itself, but also things like ions are hydrophilic. If we take a look at something that is organic that can dissolve in water, we'd be looking at something like an alcohol. So alcohols actually have a range of when they are soluble versus insoluble. Take, for example, methanol, right? It has a single carbon, it has that oxygen and that hydrogen. It is soluble in water. However, as you extend that carbon chain, say to something like butanol, it suddenly goes from completely soluble to slightly soluble. Even further, let's say that you took that chain and you really made it longer to something like octanol. Octanol is actually insoluble in water. The question becomes why? Well, if we take a look at methanol, it has that alcohol on it, that OH, that can actually do a favorable hydrogen bonding interaction with water, right? And so this is a favorable interaction. It's a favorable hydrogen bond in water. On the other hand, we know that the carbon does nothing and it remains hydrophobic. But overall, the single carbon is not enough to overpower the fact that we have those favorable hydrogen bonds. On the other hand, as we move over towards octanol, octanol does have favorable interactions with water, right? It does have these hydrogen bonds between the alcohols. So we would say that this interaction right here is favorable. However, it has this big old carbon chain over here, which has no favorable interactions. Of course, based on what we see up here saying it's insoluble, that actually outweighs the favorable interactions it's having with water, right? And so essentially what this boils down to is it gives us an interesting idea. Because if butanol is only slightly soluble, methanol is soluble, octanol is insoluble, we end up with this little quote unquote rule, which is called the rule of three. Essentially what this states is for each oxygen, you can have three carbons and be soluble in water. And again, this is a general rule. All right, there is no hard and fast statement here. This is just a generalized statement. So if we take a look up here, keeping that in mind, right, if the rule of three is true, then we would expect propanol, right, which has three carbons to the single alcohol, be soluble. And as a matter of fact, it is completely soluble in water. But then as we move to butanol, which is four carbons, it becomes less soluble. So this actually gives us a good framework for looking at these types of interactions. Because if we have something like isopropanol, this has three carbons to the one oxygen. This is indeed soluble, right? If we then take something like phenol, right, this one has six carbons to the one oxygen. This one, of course, is insoluble. Too many carbons to oxygens, it outweighs the rule of three. An interesting set of things is keep in mind that I did say oxygen on the rule of three, because in this case we have something with four carbons. It has two oxygens. This ends up being soluble in water, right? It doesn't have the same type of hydrogen bonding interaction where it can donate a hydrogen bond, but it can still accept, right? You can imagine if water were here, it could form a hydrogen bond with that oxygen, but there's no hydrogen bond to give back. So essentially, ethers still work because despite not having an OH, it can still act as a hydrogen bond acceptor. All right, so it can't hydrogen bond as well, but it can hydrogen bond okay. Looking at a couple other things that we can use this rule for, acetone, which I know you all have used in lab, has three carbons, and you may notice that acetone is completely soluble in water, right? The rule of three still fits there. Tert butanol, which has four carbons, goes from being soluble to only being slightly soluble, right? This is one where it's right on the edge of being soluble and insoluble. And that fits with the rule because it does have four carbons to the one oxygen. On the other hand, something like dioxane, this here, has four carbons, has two oxygens. This is soluble. On the other hand, if we take something like this THF, which has four carbons to the one oxygen, it is slightly soluble. So you can see where this ends up giving us a good idea of what can be soluble in water and what can be insoluble. All right. Looking past this, though, we can also talk about the solubility of amines. And this one does not follow as simple of a rule, right? Nitrogen's a little different because let's say we looked at this right here, triethylamine, which we see has six carbons to the one nitrogen. Weirdly enough, this is soluble in water. The question is why? Well, if we think about nitrogen in general, right, and we look at something like NR3, we would say that nitrogen is generally more basic than oxygen. right? Because it is less electronegative. What this what this ends up doing for us is in water where we want to be a hydrogen bond acceptor and donor. For example, this amine doesn't have any donation ability, but it does have some accepting capability. This is actually a stronger hydrogen bond than oxygen can make. Now, don't be mistaken, right? This sounds like it's a little different from what we had discussed up here, where we said that the OHs can form stronger hydrogen bonds than the NHs. I can see why this would be a little bit of a confusion, but keep in mind it is what it is interacting with, right? Up here, these alcohols are interacting with each other. And so the reason their hydrogen bonds are strong is because they both have the same type of dipole. Versus the amines both have the same type of dipole and it's weak. Down here, when we look at the water interaction, this dipole between the oxygen and the hydrogen is still the same no matter if we're interacting it with another oxygen or a nitrogen. But the nitrogen here is more basic and more willing to act as a hydrogen bond acceptor, right? Normally, nitrogens are less willing to act as a hydrogen bond donor, but they are more willing to act as a hydrogen bond acceptor. So, essentially, what this means is amines have higher water solubility due to being better hydrogen bond acceptors. All right. So with amines, it's actually very difficult to give a solubility rule, right? It's not as simple as with oxygens where you can give it the rule of three. On the other hand, amines are generally relatively soluble. They can become insoluble, but what makes it difficult is the next part that we're going to talk about, which is anions and stability. So the solubility of anions is already very well described, right? We saw that in water, something like sodium chloride is very soluble. Now, if we're thinking about this in terms of our actual organic molecules, some things can be ionic and still be soluble. So, thinking about this, first let's think about something like acetic acid. Based on the rule of three, we would say that this is a soluble compound, right? There's two carbons, there's two oxygens. It's very soluble in water. But then something like benzoic acid, it has two oxygens, but it has seven carbons. So it breaks the rule of three. We would say that it is slightly soluble, but in this case, we're going to say insoluble because it really is low solubility, surprisingly. What happens is if we were to take benzoic acid and perform an acid base reaction with it, which I believe was actually the first lab that you all did, right? If we toss in some sodium hydroxide to this insoluble benzoic acid and water, we do this reaction. What we end up seeing is, of course, the most acidic proton is the one on the carboxylic acid, and then we have sodium hydroxide, which is a base, comes in, deprotonates that. Suddenly, this is soluble in water. And it's because we've made an anion, right? And looking at this, what we see is that in water, this anion, just like we saw with the chloride from the sodium chloride solubility at first, is it can get surrounded by water that can form stable hydrogen bonds with it. And so this is just another set of favorable interactions with charge. And this brings up another really useful rule in organic chemistry that does end up kind of governing a lot of what you've been doing in lab, right? Because in lab, you've been doing some extractions, and the extractions normally follow this sort of rule of charges, which states that charged molecules are always soluble in water, which is very hard to think about sometimes because there is a large set of molecules that can be huge but still be soluble in water as long as they are charged. Now, with that being said, there are some weird properties that things have, like making micelles, that don't necessarily remain true in terms of saying that they're always soluble in water, but they still work at being soluble most of the time. So, generally speaking, these things are going to be soluble in water. And this is very important for biochem because if we're thinking about different things in the body, a good chunk of your body has phosphates, right? And these phosphates are usually attached to organic backbones, but overall, the phosphates have two charges. These are soluble. Same thing with carboxylates. There are a lot of carboxylic acids that are in your body. If they get deprotonated and they form these carboxylates, we would say that these are soluble. Furthermore, if we're looking a little bit further down the line, we have protonated amines or ammoniums, and these are also soluble. Thing with the ammoniums as well, and the reason that I was beating around the bush a little bit when we talked about amine solubility, is at pH 7.4, almost all amines exist as ammoniums, right? And the reason is their pKa. The pKa of that NH is right around 10. So having a pH lower than that means it's more acidic, it's going to be protonated, right? So in reality, when we're talking about amines, it's hard to say whether or not they're actually soluble in water just because they're able to do those more favorable hydrogen bonds, or if it's also due to the fact that you're forming more ammoniums, which are very soluble in water. That being said, for each of these species, these are all easily generated by acid-base chemistry. Okay? So overall, when we're talking about a lot of these different types of interactions, a lot of it boils down to, is it a favorable interaction with whatever we're looking at? If so, it's probably going to be soluble. If not, it won't be. So with that being said, that is everything for physical properties that we need to go over for this course. So this is it. The end of the material that you need for the ACS final exam. So I would make sure that you're studying for it. I'd make sure that you really crack down on it because remember that this exam will not have any test corrections or anything like that. So the score that you get will be the score that you get. So with that being said, I will see you next time, which will be on Friday for an in-person lecture so that we can review some of the more challenging concepts that we've gone through throughout this course. And then we'll close it out by taking that final exam. See you then.